Hello. I'm delighted to be here, sort of being the opening act for Guy Metcalf's presentation, Chaotic Mixing, the first 25 years. It's sort of unbelievable that it has been 25 years since the Kinematics of Mixing appeared. The book was written sort of quickly, 6 months is all that it took in Caltech. And before that, shortly before that, there was a paper in Nature that appeared in June before the publication, and one in Scientific American. One of these papers made it into the book, Nature, the other one did not. And after the book appeared, there was more research, some of which took us into mixing of solids. Another book took us more in the math side of things. But at some point, the picture became clear as to what the essence of mixing was. And the essence of mixing is that if you have a domain and you have an initial condition in here, and this is transformed in some kind of motion, part of the initial condition in here comes back in a folded way. And it became clear also that if you have a flow, like a cavity flow, and you move one boundary and you have a streamline like this, and then you flip it and you move the lower boundary and the streamlines become like that, if you put the two together and superpose it, there will be a crossing of streamlines, and that in itself is the essence of what a flow that could be chaotic looks like. So if you have the flow in here where you put initial conditions strategically located, one in here, the one over there, and you let the flow advance, you will find that there is folding with one of the initial conditions, and this will be exponential. If you fold it once, you can fold it again because this is a repetitive action. And nothing much will happen with the other initial condition. It stays basically in the same location. But if you follow it as it moves along, you'll find that that island of where nothing much happens kind of moves as a whole and eventually returns to the initial location. So once you have done this for a time periodic flow, it's not hard to imagine how you can do it for an spatially periodic flow. And in here you have a flow which is spatially periodic. It has a series of obstructions and is the same everywhere. It's a series of obstructions that are periodic. And you can have initial conditions that mix. And if you're strategic about locating the other initial condition, you will see that you can make it stay within an island and it will not mix. So once we had this essential picture here, the stretching and folding as being sort of the fingerprint of chaos, we could imagine by the year 2000, when this review and this picture appears in here, what kinds of things will be affected by these kinds of thinking. And we could put things in the environmental side, oceanography, polymer engineering, but we miss a whole bunch of things that were about here. Very low Reynolds number, very small scales, and it was something driven by technology, and that was microfluidic applications. There have been an explosion of work in microfluidics, and I would say of the 2,500 times that the kinematics of mixing references are up to now, a good fraction were driven by microfluidics. Now, what I enjoy in this journey is encountering a topic that was fragmented. There were lots of examples about mixing. They all look different. They all look messy. But at some point, you go to this sort of encapsulation of the essence of the problem, and this is this picture, the stretching and folding picture. And from there on, what is really interesting to follow is the divergence of how this picture can have strands in multiple application areas, the ones that I mentioned before. There are many of them. Some of them involve how reactions or competitive reactions may be affected by the flow. Some of them may involve how droplets get broken by the flow and how some are not. Aggregation process, fragmentation process, a myriad of applications. And I cannot imagine anybody better to explain those multiple applications than Guy Metcalf. Thank you.